Guys, you're welcome to today's teaching. I want to believe you are fine. I want to believe you are doing fine. I want to welcome us all to today's class. This is chemistry hangout. Today, I want us to pay maximum attention. Yeah, I want us to pay maximum attention because I'm going to do a very interesting topic. I've seen a lot of people find this topic difficult. I've seen students struggle. They are struggling with this very particular topic, how to do the calculations. And I want to give an explicit explanation about this very particular topic. So I want to believe you are ready for today's class. If you are just watching this YouTube channel for the very first time, kindly click on the subscribe button and click on the notification bell so that when I upload any video, you are going to be notified. This is going to be a very wonderful class. I want you to pay maximum attention. And the topic today is the law of combining volumes. The law of combining volumes. This is a very interesting law. Yeah, it's a very, very interesting law. And I've seen a lot of students do it wrongly. I've seen a lot of students struggle with this very particular law. Of course, this law is still from the kinetic theory of gas, and we are going to be taking a full explanation of this. Under the law of combining volumes, we have two laws put in one. Yeah, we have two laws. We have a law called the Gay-Lussac's law. We have a law called the Gay-Lussac's law, okay? And we have the second one called the Avogadro's law. I will explain the reason why these two laws is put into one and we consider them as one. Because this very particular law of combining volume, it was Gay-Lussac that first postulated his law. Okay, and what was the law Gay-Lussac postulated? Very interesting laws, very wonderful law. Gay-Lussac's law. Let's see Gay-Lussac's law. What is the law Gay-Lussac postulated and what is the shortcoming of Gay-Lussac's law? Now, for Gay-Lussac law, it states that Gay-Lussac law states that, okay, when gas reacts, Gay-Lussac law states that when gases react, please take note of this. When gases react, okay, they do so. When gases react, they do so in volumes. They do so in volumes. They do so in volumes which are simple ratio. Which are simple ratios. Which are simple ratios. Okay, when gases react, they do so in volumes which are one another. Simple ratios to one another. To one another. Okay? To one another. And to the volume of the product. And to the volume of the product and to the volume of the product if gaseous provided that temperature and pressure remains constant, provided that temperature and pressure remains constant. Provided that temperature and pressure remains constant. So this is your Gay-Lussac's law saying that when gases react, they do so in ratio, okay? They do so in volume, which are simple ratios to one another, and to the volume of the product, if gaseous, provided that temperature and pressure remain constant. What is the meaning of this Gay-Lussac's law? What is Gay-Lussac saying here? Yeah, what is Gay-Lussac really saying here? What's the meaning of this Gay-Lussac's law? And what is it actually saying? Let me give further examples, let me give further explanations. Don't forget the law that when gases react, they do so in volumes which are simple ratios to one another and to the volume of the product if gaseous, provided that temperature and pressure remains constant. So what is Gay-Lussac saying? Let's take for example now. Gay-Lussac said that if I have hydrogen gas, okay, reacting with chlorine gas to give us hydrogen chloride, right? If you look at the equation is not balanced. If you look at the equation is not balanced. So what do? We balance the equation. So we have two hydrogen here, we have two chlorine here, so we can have two. We understand balancing of equation. So the equation is now balanced. I want to believe this is clear. So we have two hydrogen here, we have one, we have two hydrogen molecules here, we have two chlorine molecules here, but we have two molecules of hydrogen chloride. Now, what is this very particular law saying? What is this very particular law? What is this very particular Gay-Lussac law saying? It's saying that one volume to one volume of this we give two volume of this. What is it taking into consideration? It's taking into consideration the it's taking into consideration the volume, which are the coefficients of each very particular reaction. If you look at this, you have an invisible one here. If you look at this, there's an invisible one here. If you look at this, there's an invisible one here. Then you have this place to be two. So that's what your Gay-Lussac law is saying. That's what Gay-Lussac law is saying, that the reaction of this hydrogen plus this chlorine to give us hydrogen chloride is that one volume of hydrogen, one volume of this hydrogen gas, okay, is reacting with one volume of this chlorine gas to give us what? Two molecules of hydrogen chloride gas. I want to believe this is clear. I want to believe this is very, very clear. So what Avogadro's is saying is that these very particular reactions, they are reacting in volume, meaning one volume of hydrogen gas is reacting with one volume of chloride gas to give two volume of hydrogen chloride gas. Let's take further example. I want us to get this law. If I have hydrogen gas again plus oxygen gas giving us H2O, that's water in form of steam. Now let's look at this. Let's balance the equation. Hydrogen is what? Is 2 here. Hydrogen is 2 here. Balance hydrogen is 2 here. Then we can have 2 here to balance oxygen, right? And we can balance our hydrogen with 2. Now, if you look at this, according to Avogadro's, if you look at this, the meaning of this is that we have two volume of hydrogen gas, these two here, that's what we are considering. Two, we have an invisible one here. So to one volume of oxygen gas, they are reacting together to give us what? Two volumes of water, of steam. I don't know if this is very clear. I want to believe you are following me. So the law, Gay-Lussac is saying that when gas reacts, and that's why if you check all these things that are reacting, they are for gases. When gases react, they do so in volumes, which are simple ratios to one another and to the volume of the product if gaseous, provided that temperature and pressure remains constant. I want to believe this is clear. I want to believe this is clear. Let me take another example. Let me take another example. And that's why we have to understand this law. We have to take our time to to understand this law. Let's take another example again of what Avogadro is actually, of what Gay-Lussac is actually saying. What's Gay-Lussac saying? If I have nitrogen gas, okay, plus hydrogen gas giving us ammonia gas. Okay, so let's balance the equation. Very, very important. Let's balance the equation. I can have 2 here, becomes 2 nitrogen. Then I have 3 here to balance up the hydrogen. So we have 2 nitrogen, 2 nitrogen is also here. Then we have 6, hydrogen. Then we have 6 hydrogen here. Now, what is the volume of which they are reacting now? What is the volume of which they are reacting? The volume ratio now will be 1, okay? Can you see that now? 2 what? To 3, right? And to what? To 2. So which means they are reacting in 1 volume, 3 volume, and 2 volume. I want to believe this is very clear. I want to believe this is very clear. Very, very clear. Let's do another one again. Very, very important. I'm just doing all this for us to understand all this. Very, very, so that we can understand Gay-Lussac law. Then we can use it, we can now use Avogadro's to now interpret what Gay-Lussac is saying. Then we can now take questions on them. So that is just what your Gay-Lussac law is actually saying. Let's take another example, the last example. Here I have carbon 2 oxide gas reacting with oxygen gas to give us what? CO2 gas. Let's balance the equation. CO, one carbon balance. But here we have how many oxygen? We have 2 here, right? Plus 1 here, that is 3. So I can put 2, I can balance this with 2, okay? And balance this 2 with 2. So let's check it now. 2 carbon here, 2 carbon here, 2 carbon here, balance 2 oxygen plus 2 making 4, then 2 plus 2 making 4. So what are the volumes by which they are what? They are combining now. Somebody should be able to tell me this yourself. Okay, let's go. 2 right volume to what? To 1 volume, okay, then to 2 volume. And that's what your Gay-Lussac law is saying. So the Gay-Lussac law is saying that when gases react, they do so in volumes which bear simple ratio, right? Which bear simple ratio to one another and to the volume of the product. So both the reactants is coming together to give the product. So they bear simple ratio to the product too, provided that temperature and pressure are what? Are constant. This is what your Gay-Lussac law is saying. But your Gay, one of the problem with Gay-Lussac law then when Gay-Lussac is that he was not really able to use kinetic theory to explain this very particular law. That was one of the problems he encountered. He did not actually use the the this very particular law. He could not really relate it to the kinetic theory of gas. And if you have taken your fundamental chemistry classes, you will know this your Boyle's law, your Charles law, your Darcy law of partial pressure. They are still explaining, they are using the law to explain kinetic theory of gas. So Gay-Lussac could not use this very particular law that he postulated to explain kinetic. He could not use kinetic theory to explain his law. And ideally, if the gas is an ideal gas, he should be able to use kinetic theory of gas to explain the behavior of gas. I want to believe this is clear. So it was Avogadro's that now explained what Gay-Lussac law is saying satisfactorily. Yes, to scientist satisfaction, it was Avogadro that now explained the law Gay-Lussac has put forward and now show us the relationship between this very particular Gay-Lussac law and use kinetic theory of gas to explain it. So what is Avogadro's law? What did Avogadro's law say? So what did Avogadro's law say? Avogadro's. What did Avogadro's law? Said Avogadro's law says that or states that Avogadro law states that equal volume equal volume equal volume of all gases equal volume of all gases at the same temperature equal volume of all gases at the same temperature and pressure contain same number of molecules. This was Avogadro's postulation that equal volume of all gases at the same temperature and pressure contain same number of molecules. Now, what is the meaning of this? What Avogadro is saying here is that your volume of all gases at same temperature and pressure contain the same number of molecules. So what Avogadro is saying is that your volume is still equal to what? Is equal to number of moles. That's what Avogadro's is actually saying. And look at what Avogadro's now postulated and now explain the postulation of Gay-Lussac's. Don't forget we did something like this. hydrogen gas, okay, plus chlorine gas at the beginning, giving us this, and we know we balanced it. We get that now, we balanced it. Now for Gay-Lussac law, for Gay-Lussac's, for Gay-Lussac's law of combining volume say you have here to 1:1:2, and that is what is in volume. I want to believe this is clear. That is in volume. But now Avogadro's, what Avogadro's is saying is that this one volume is still the same thing as saying one molecules. It's still the same thing as saying one molecules, and it's still the same thing as saying what? Two molecules. I want to believe this is clear. I want to believe this is clear. Two molecules. Can you see? So for Gay-Lussac law is talking about this in terms of volume, while Avogadro is talking about this in terms of molecules. Can you see that now? So what is actually what Avogadro is now saying, that volume 2 at constant temperature and pressure is the same as the number of molecules. As the number of molecules. Let's take another example before we now look at the calculation aspect. So we did another one, we did hydrogen gas, okay, plus oxygen gas, giving us what? H2O. This is gas, balancing the equation. We have 2 here and we have 2 here. So according to Gay-Lussac's, okay, Gay-Lussac said this will be 2 volume, combining volume, this will be 1 volume, and this will be 2 volume, okay. Why for Avogadro's? For Avogadro said this your 2 volume is still the same thing as 2 molecules. This your 1 volume is still the same thing as 1 molecules, and this your 2 volumes is this the same thing as 2 molecules. Can you see that? So that's what, and that's why this law is now better understood, because your Avogadro's can now relate it, can use kinetic theory of gas to actually talk about it. And that's the reason why, if you have seen the ideal gas equation, you will see that it is the combination of Charles law, combination of Charles, Boy's law, and then Avogadro's law. So it was able to, and that was what gave us the PV equals to nRT in ideal gas equation. So it was this Avogadro's law that now explained Gay-Lussac's law. And of course, Gay-Lussac was not able to use kinetic theory of gas to explain the combining volume that he's talking about. But little did Gay-Lussac know that your volume 2 is still equal to the number of moles, and that's why Gay-Lussac is the one that now explain what Avogadro's is the one that now explain what Gay-Lussac law is actually saying in his own law. You understand? Because he is saying that when gas react, they do so in volume by a simple ratio to one another. But Gay-Lussac law is now saying, yes, you are correct, because the number of volume is equal to the number of molecules. So if you have 2 volume, you have 2 molecules. If you have 1 volume, you have 1 molecules. And then Avogadro was now able to use that very particular law he stated, which is relating volume to molecules, to now postulate the kinetic theory of gas. He used kinetic theory of gas to explain it. And that's the reason why we now have this. So the ideal gas equation is the combination of what? Combination of Charles, combination of Boyce, and combination of what? Avogadro. I want to believe this is very, very clear. I want to believe this is very, very clear. Now, there are a lot of questions that come from this law, and I've seen a lot of students do it wrongly. Yes, I have seen a whole lot of students do it wrongly. I tell you, sincerely speaking, you can solve Avogadro's law questions on Avogadro's and Gay-Lussac's in few minutes. And I mean that in few minutes. Now let's take some of the examples like the way I normally do. We're going to be taking from job, we're going to be taking from WAEC past questions, from IGMB past questions, so that we will see how it works. Now, very, very important, note these words. And these are words that these are words that make you know the question they are actually asking you here is what is either is law on the Lussac'S law or Avogadro's law, because the two is combined to actually form one. I want to leave that square. So when you see statements like sparked, note this, let me write, note this statement or these words. Let me say, note these words. Let me pick an eraser here. Note these words. Very, very important. When you see those words, just know that the probability that the question is going to be question of this very particular law is very, very high. So you note this, you note this like part, very, very important. You note, words, note words like no one can see sparked. This word, very, very important. You see something like this very particular gas or hydrogen gas is sparked. Note this word. Note this word. Excess, excess gas. Note this word. Excess gas. Very, very important. Note this word too. Unused, unused gas. Very important. Unused gas. This one too is common. This word too, very, very important. I said not sparked, not excess gas, not residual gas. All these words are words we use in, or resulting gas. All these words, when you see them in a particular the gas law is very, very, very high. You see, hydrogen gas is packed with this. Note these two, very important. Mixed. These are words that are common in questions like this. We'll take some questions. Mixed. If you see questions like this, unused, residual, all those words are words that are common for questions for this that you're made to react, made to react, and words like that. So they can use any of these words. They can use hydrogen gas is packed, hydrogen gas is mixed, hydrogen gas is made to react. Get out. So calculate the excess gas, calculate the unused gas, calculate the residual gas, calculate the resulting gas. Please, I want us to pay maximum attention to this. Please, I want us to pay maximum attention to this. Let's take examples. Examples now. Let's take example one. I'll solve around 4 or 5 examples because of time. I can take 4 or 5 then so that I can, build that confidence in us. Then we can. 70 centimeter cube, 70 centimeter cube of hydrogen, 70 centimeter cube of hydrogen is packed. Can you see that now? Can you see that? Is packed with 40 centimeter cube of oxygen. Calculate one, the excess gas, the volume of the excess gas. Okay. 2 is that volume of the excess gas, or calculate the volume of the residual. That's 2 questions in one. Calculate the volume of the residual gas. Okay, so let's take this question. Please, I want us to pay attention to this. You can solve these questions in few minutes. So let's solve this. The equation of reaction. Let's write the equation of reaction. Hydrogen gas is packed with what? With oxygen gas. Is that not? Hydrogen gas is what? Is packed with oxygen gas. Very, very important. Is packed with oxygen gas to give what? To give steam gas, right? Then we balance the equation, 2 here, then what? We have 2 here, we have 2 here. Balance. Now, please, I want us to take note of that's where the Gay-Lussac or the Avogadro's law works. It depends on the one you want to use, but it's still the same thing. Don't forget that Gay-Lussac law is saying that here we have 2 volume, right? Here we have 1, abi? Here we have 1 volume, right? And here we have what? 2 volume. Why? I'm just stating this. If you want to solve it, I'm just stating this so that you will know the significance of the Avogadro's and the Gay-Lussac law to solving this question. And your Avogadro is saying it's the same thing as 2 molecules. Some people write 2 moles, still 1 molecules and 2 molecules. I want to believe this is clear. I'm just stating that again so that you know. Now, watch this very particular ratio, which means that this very particular reaction is in the 2 to ratio 1 to ratio 2. This is what I want to bring out, but I just want you to know where I got the ratio from. So this is the same thing as saying 2 to ratio 1 to ratio 2. Are we together now? Now, what is the combining volume we are giving? The combining volume we are giving. The combining volume. Like we have in the question, the combining volume. What's the combining volume we have in the question? The combining volume for hydrogen gas, you can see they gave us 70 centimeter cube. So here, 70 centimeter cube, right? For oxygen, they gave us 40 centimeter cube. Why they didn't give us for this? I want to believe this is clear. Now check this. Look at this. 2 moles of hydrogen, 2 moles of hydrogen or 2 volume of hydrogen is reacting with what? With 1 mole of oxygen. Meaning for every 2 volume of hydrogen, we need 1 mole of what? We need 1 mole of oxygen. I want to believe this is clear. For every 1 mole for every 2 moles of hydrogen gas, we need what? 1 mole of oxygen gas. I want us to get the reacting volume now. We are getting the combining volume, but how do we get the reacting volume? Take note of these very particular numbers I circled. 2 to ratio 1. You see that? Now, if the reaction is in 2 to ratio 1, if the reaction is in 2 to ratio 1, it means that if I am using 70 centimeter cube of hydrogen, what volume of oxygen will I be needing? If I use 70 centimeter cube, since the reaction is 2 to ratio 1, for every 2 volume of this, I need 1 volume of this. Can you see? So if I use 70 centimeter cube of hydrogen gas, what mole of oxygen gas will I be needing? I will need what? 35. Look at that. I will need 35. Don't forget the ratio is in 2 to 1. Do you see that now? So if I'm using 70 centimeter cube, if I'm using 70 centimeter cube of this, then I will need 35 centimeter cube of this. I want to believe this is very clear. Can you see that now? So the reacting volume is going to be 35. The reacting volume means that if I use 70 centimeter cube of this as given in the question, I don't need 40 of this. I only need 35 centimeter cube of this. I don't know if you are getting this. And then I will be needing what? 70 centimeter cube of this too. Why? Because this is 2 to what? To 2. Can you see that now? This is 2 to what? To 2. Or how can you get it again? This 35, just multiply it by 2 by the ratios. 35 times 2 is going to give us 70. 35 times 1 will give us what? 35. And 35 times 2 will also give us 70. Can you see that now? So from here now, since very very important, you see this very particular ratio is very very important, very very important, and that's where your Avogadro's and Gay-Lussac law is coming in. This 2 to 1 is important. So if I'm using 70 centimeter cube of this, I need only what? Only 35 of that. Now the question is now saying, so from here now, it means that what is the volume remaining here? We don't have any volume remaining here because 70 is used up, so we don't have any volume remaining here because this is 70 and we use the whole of the 70. But for this one, what is remaining? We have 40 already as given in the question, but we use 35. So here will be remaining 5 centimeter cube, right? And here will be remaining 70 centimeter cube. Do you see that now? So the question is now saying, what is the excess gas? There's an excess gas here. And what is the volume of the excess gas? This is the excess gas. You know, we have 40 of this, but we use 35 of it. You get that now? So the excess gas is 5 centimeter. The gas that is in excess, that is remaining, is 5 centimeter. They can ask you, is either they use the word excess or, I'm giving that excess or unused gas. Any of this word means the same. So note that you might say find the volume of the unused gas, find the volume of the excess gas. It's still the same. Why this one is what? 70 centimeters. So the excess gas or the unused gas is what? 5 centimeter cube. Why the next question, this question 1? Why the next question is now saying we should find the volume of the residual gas. Volume of the residual. Residual means what is the volume of all the gas that is remaining after the reaction has taken place. So which means 5 centimeter is remaining, 70 centimeter is remaining. So the residual gas or the total gas or the resulting gas. Please take note of this statement. The resulting gas. So it's either they use the word residual gas or they use the word total gas or they use the word residual gas. I want to believe that is very very clear. So very very important. This will now be the 5 centimeter that is remaining and the 70, the 5 and the 70. So this will be 5 centimeter cube plus 70 centimeter cube, and that will give us 75 centimeter. I want to believe this is clear. Please go over this thing over and over again. I'll still do some examples. I'll do like 2-3 examples so that we can understand this. Very very important. I'll do 2 or 3 examples so that we can understand this. Very very important. So that we can get it. These things are very very simple. I tell you, they are very very simple. But just understand it and you know you become a professional. You solve it like a pro. You solve it like a pro. Example 2. Let's see example 2. So you solve all these things like pro, like in few seconds for Jambite. In few seconds, you should be able to tell us what your answer is in like few seconds. And I mean it, in few seconds, you should be able to tell us what your answer is. You should be able to tell us what your answer is. So I'll take another question now. I'll take another question, still explain it so that we will understand what this very particular question is like and how we can actually solve it. Very, very important. Now, another question, they said 30 centimeter cube. They said 30 centimeter cube. They said 30 centimeter cube, okay? 30 centimeter cube of carbon 2 oxide. Of carbon 2 oxide. 30 centimeter cube of carbon 2 oxide. That's CO. They gave us sparked. I see. Are sparked, are mixed. Just know that it's question on Avogadro's and Gay-Lussac. Are sparked with 30 centimeter cube of oxygen. With 30 centimeter cube of oxygen. If all volumes are measured at STP, if all volumes are measured at STP, okay? Calculate. The volume, calculate the volume of one, the unused gas, or they can tell us the excess gas, right? While two, the residual or the total gas, the residual gas. So let's take that and see solution. Okay, let's go now. Let's go. The first thing is, please, you have to understand equations, writing of equations. If you have not actually, if you have not actually watched those videos, I have done those videos, very, very important. So we have our carbon 2, that's CO, as packed with oxygen, that's CO2, then it's giving us what? CO2 gas. Right? CO2. Then balancing the equation very quickly, you can have 2 here. I've done that even in my previous example 2. So very, very fast now. Let's go. This will be 2 to ratio 1 to ratio 2 according to Avogadro and Gay-Lussac. This will be 2 to ratio 1 to ratio 2, right? And in the question now, what is the combining volume? What's the combining volume? The combining volume, that's the volume given in the question. Let's scroll up. Okay, 30 centimeter cube. 30 centimeter cube of carbon 2 and 30 centimeter cube of oxygen. So the combining volume is 30 centimeter cube of this and 30 centimeter cube of these two. Please pay attention to the ratio now. Look at it, the reactants now. For the reactants, we have 2 of CO to 1 of O2, which means for every 2 volume of this, we need 1 volume of this. Can you see that now? So go back to the equation. If for every 2 of this, we need 1 of this, meaning for every 30 of this, what are we going to be needing? Somebody watching this video, can you just suggest that? Can you tell me that? What volume are we going to be needing? We are going to be needing 15 centimeter cube. So if we need 30 of this, then we need 15 of this. Why? Because it's in 2 to ratio 1. Can you see that? So if we need 30 of this, I want to believe that's clear. If we need 30 of this, so the reactive volume now, the reactive volume, if I need 30 centimeter cube of this, which means I'll be needing 15 centimeter cube of this. Then I'll be needing 30 centimeter cube of this too. Why? Because it's 2 to ratio 2. But the reason why we have 15 here is because this is 2 to ratio 1. I want to believe that is clear. So from there, we now have that this one is used up, 30 is used up. This minus this, that will give us 15 centimeter cube, and this will be 30 centimeter cube. I want to believe this is very clear. I want to believe this is very clear. So from here, they said volume of one, they said volume of unused gas. Volume of unused gas. So the volume of unused gas here, do you see that we have 30 centimeter cube of this? Then from there, we now got 15 centimeter cube of this, right? So the volume of unused gas is 15 centimeter cube. Very important. Why the volume? That's the second one. The volume of the total gas or the residual gas is now going to be this 15 plus this 30. Then we now have 15 centimeter cube plus 30 centimeter cube. And that will give us what? 45 centimeter cube. So let's go up again to see some of those questions. So this is the question and that's the solution. Let me try and take one again. Let me take one again so that I can leave you guys to your destiny. I leave you to your destiny to do your own work. So let me take one example here again. Let me take one example. Okay, let me take this example. Okay, I love this. Let me take this example 3 now. Example 3. So I think I'm taking another question here. Okay, let me take 3 first. Then I'll take another one. Example 3 is 50 centimeter cube. Okay, 50 centimeter cube of hydrogen. 50 centimeter cube of hydrogen as packed. Look at that statement. When you see that statement, sparked, mixed, react, then know they are coming from Avogadro's angle. With 50 centimeter cube of hydrogen as packed with 20 centimeter cube of oxygen at 100 degrees Celsius. At 100 degrees Celsius. Okay? At 100 degrees Celsius. And 1 atm, that's 1 atmosphere. That's a unit for pressure. Okay. Calculate. Oh, okay, this one they gave us options. Calculate the volume. Calculate the volume. Calculate the volume of residual gas. Okay, they gave us options here. Calculate the volume of residual gas. A, they gave us A, 50 centimeter cube. B, 50 centimeter cube. B, 10 centimeter cube. C, 40 centimeter cube. D, 30 centimeter cube. And E, they gave us 70 centimeter cube. So this is another question. This is another question, very, very important. And they ask us to calculate. It's not what they ask you to calculate. Like you don't make mistakes. They ask us to calculate the residual gas, meaning they are actually asking of the total gas. Okay, not the excess, not the unused. So let's go. Let's start the equation of reaction like we normally do. Hydrogen gas is reacting with what? With oxygen gas. Then it will give us this H2O. I want to believe this is clear. So from here, we balance the equation 2. We balance the equation 2. So according to Avogadro'S, Gay-Lussac's, they said this is 2 ratio 1 to ratio 2. I hope this is clear. Then, what is our combining volume? What is our combining volume? As given in the question for hydrogen, we have 50 centimeter cube. Please pay attention to this. For hydrogen, we have 50 centimeter cube. For oxygen, we have 20 centimeter cube, right? They didn't give us for this. Now look at this. Please pay attention to this now. This is very, very interesting. Pay attention to this. And that's the reason why I had to use this particular example. Now, if you look at the hydrogen they gave us, first of all, know that this is 2 to ratio 1. Hydrogen, this is for 2 for hydrogen, 1 for oxygen. Let me write the oxygen so you don't think I wrote 10. 1 for oxygen. Now, they now give us 50 centimeter cube of this. Which means if I'm using 50 centimeter cube of this, oxygen that will be needed will be what? 25 centimeter cube. Can you see that? But look at the volume they gave us in the question, 20. The volume they gave us is not up to 25 because ideally, if 50 of this is reacting, if 50 of this is combining, we need 25 centimeter cube of what? Of oxygen. But the oxygen they gave us in the question is 20, which means we cannot use 50 of this because 50 of this is going to give us 25 of this. And here is not up to 25, which means that we are going to use this 20 because that is the available volume that is what? That is available. That's the available volume that is available. Which means that if I'm now using 20 centimeter cube of this, get that now. If I'm using 20 centimeter cube of oxygen now, how many hydrogen am I going to use? 40 centimeter cube. I want to believe this is clear. So the reason why we cannot use this 25 is because the available volume in the question is 20. Can you see that now? So I'm to use this 20. I cannot use 25 because the volume available is not up to 25, it's up to 20. But if I use 20, it will affect this volume too because I'm not going to be using, I'm not going to be using 50 again. I'm going to be using 40 because 2 to ratio 1. If I'm using 20 of this, I'll use 40 of this. So which means that the reactive volume, here is now going to be 40 centimeter cube. Here will be 20 centimeter cube. And here also will be 40 centimeter cube. Why will it be 40? Because this is 2 to ratio 2. So the same thing here will be what is here. I want to believe this is clear. So as we move further now, let's now see. Okay, we have 50. 50 is available, we use 40. So here will be remaining 10 centimeter cube. 20 is available, we use all 20. Nothing will be remaining here. Then 40 centimeter cube will be here. And the question says what? The question says calculate the volume of the residual gas. That's the question. Calculate the volume of the residual gas. So if you calculate the volume of the residual gas, what's the meaning of volume of the residual gas? The volume of the residual gas means that we are calculating all the volume that is remaining. If they have asked us to calculate volume of the unused gas or excess gas, it will be 10 automatically. But now we are calculating volume of the residual gas. So it is going to be 10 centimeter cube plus 40 centimeter cube. And that's going to give us what? 50 centimeter cube. So the answer here is what? Is A. I want to believe we are getting this. The answer here is what is A. The answer in that question is what is A. Let me take the last example and I'll be done. Then I'll give you one to just try yourself. Get that? I'll give you guys one to just try yourself so that you can gain, you can gain confidence in this very particular one. So that'll be example what? I think the one I did here is example 2, I guess. Am I right? Okay, example 3. So meaning this will now be example 4. This will be example 4. So that is how Avogadro's law works. That's how it works. Example 4. Example 4. Now for example 4, the is here. And the question is 10 centimeter cube. Okay. 10 centimeter cube of CO, that's carbon 2, is mixed. And sparked and sparked and sparked with 100 centimeter cube of 100 centimeter cube of air, right? Of air, 100 centimeter cube of air containing 21% of O2, right? If all volumes, if all volumes, if all volumes are measured, if all volumes are measured at STP, right? Full stop. The volume of resulting gases, can you see that statement? That's the total gas remaining. Of resulting gases would be A, would be A. Here I have 90 centimeter cube. B, I have 100 centimeter cube. C, I have 105 centimeter cube. D, I have 110 centimeter cube. And E, which is the last option, I have 115 centimeter cube. Very technical questions. You have to just be careful. When you are solving questions like this, you have to be very, very careful. So let's go over the question, try to solve it, and let's see. The equation of reaction here, the equation of reaction here, the equation of reaction. Now listen to the question. They said 10 centimeter cube of CO is mixed and sparked with 100 centimeter cube of air. It will interest you to know that in air, you have different mixtures there. That's where the question start testing your knowledge of your fundamental chemistry. So in air, we have oxygen. I hope you are aware. We have nitrogen. I hope you are aware. We have moisture. I hope you are aware. We have some rare gases. I hope you are aware of all this. And we have CO2 too. Do you get that? So in air, you have all this. But when you are burning something, when you burn something in the presence of air, the dominant mixture that is actually at work there is oxygen. That's what supports burning. Do you see that? So that's why the question is saying 10 centimeter cube of CO is mixed and sparked with 100 centimeter cube of air. In air, nitrogen is not supporting your burning. Red gas is not supporting your burning. What is actually supporting your burning is oxygen. So take note of that. And the percentage composition of oxygen in air is around 21%. And when you say 21%, that is 21 over 100. So when you add all the mixtures in air, your oxygen 21, your nitrogen 78, your CO2 is around 0.02. When you add all those things together, it's still going to give us what? 100. So we need to get the composition of air in that air first, which will now give us the volume of air that is reacting, because it is not all the air that is reacting. So from there we can now say, let's get the volume of air that is the volume of oxygen, right, in air that is reacting. So from there we can now do 21 over 100 times what? 100. Because if you add up all these mixtures in air together, we are going to get 100, okay? And you have oxygen to be 21%, so 100 will cancel 100. Then the volume of oxygen that is actually reacting is 21 centimeter cube. So note that, very important. This is the volume of oxygen that is reacting. So let's now move further. Then we now have, let's write the equation of reaction first. So we have CO, that's carbon 2 gas, plus oxygen gas, that will now be CO2 gas. Balancing the equation, we have 2 here. Okay, that's 2 carbon, 4 oxygen, we have 2 here. I want to believe this is very clear. Now, according to Avogadro, so you already know, let me write this because I want to scroll down. We have 10 centimeter cube of CO, and we have what? 21 centimeter cube of oxygen to be the combining volume now. So let's scroll up. Then we'll come and choose the options when we are done with the question. Let's hide the options, then when we are done with the question. Now, according to Avogadro's, what are we having here? That's 2 to ratio 1 to ratio 2. Can you see that now? 2 to ratio 1 to ratio 2. Then the combining volume as given in the question, for carbon 2, we have 10 centimeter cube. For oxygen, we have 21 centimeter cube. And for this, we are not giving the volume. So, look at the ratio. Please pay attention. This is the key moment in questions like this. You see, this ratio is the key moment. Now let's go to this place now. 2 of CO need 1 of O2. Can you get that? 2 of CO need 1 of O2. Get that now? So if I'm using 2 of this, I'll be using 1 of this. Do you get that now? If I'm using 2 of this, if I'm using 2 of this very particular one, then I'll be using what? I'll be using 1 of this. So which means that if I have 10 centimeter cube of this, how many of these will I be using? Because it's still 2 to ratio 1. So if I'm using 10 of this, definitely I'll use 5 of this, 2 to ratio 1. Which means if I use 10 centimeter cube of this, I will be using 5 centimeter cube of this. Very important now. Do you see that now? Because this is 2 to ratio 1. So which means here 2 will also be 10 centimeter cube. Because if I'm using 10 of this, since it's 2 to ratio 1, I'll be using 5, not all the 21. I'll be using 5, which is now the reacting volume. This is the reacting volume. So from here, this is used up already. 21 minus 5. 21 minus 5 is going to give us 16 centimeter cube. And this will now give us 10 centimeter cube. Don't forget the question is now saying the volume of the total gas. I've said that in my explanation. They are using the word, they might use the word resulting gas, they might use the word residual gas. It's still saying the same. So a lot of students will still come here and still fumble. And let me tell you why you will fumble. That's why this is a very tricky question. Now, some students will now come and say the residual gas here, they are overjoyous. They want to come and choose option. 16 centimeter cube plus 10 centimeter cube. They will now say the answer is 26 centimeter cube. You have beautifully failed it. In fact, your suffering is in vain at this point because you have just suffered yourself. You failed it woefully. You are surprised. Okay, let me now explain why you have failed it. They say the volume of the residual gas. That's what the question is saying. You have forgotten to add up the mixtures in air. You know they are talking about air. Don't forget, out of air, you only use 21 centimeter cube of oxygen. Remaining how many? 78. Can you see? So the 78 is still there, which must be added to this answer you got. I want to believe this is clear. So the answer is going to be 16 centimeter cube plus this 10 centimeter cube, right? Plus the one that is remaining in air, because we have removed 21 out of it. So it's remaining what? 78 centimeter cube. So if you add this up, 16 plus 10, that will give us 26. Then 78 plus 26, that will give us 28 plus 26 rather, plus 76. This will give us 4. This will give us 4. Carry 1, right? 78, that's 20. Sorry, 79. 21. 21 will give us 79. Sorry, 79. So 21 minus 100 is going to give us 79. So, which means this will be 5, right? Carry 1, there's 9, this will be 10. So the residual gas that is remaining is 105. I want to believe this is clear. It's 105. So let's go to the option and see if the option is there. Okay, can you see the option is C? The correct answer is C, 105. Can you see, even you will know you are even wrong, because here even in the option you don't have 26 centimeter cube. So they expect you to know, when you are not seeing the options there, that will make you suspicious that something is actually wrong. But you have to add the remaining 79. You have to add it together. The 79 that is remaining, you will add it together to the residual gas and you will get your answer. So I want to believe you can tell other ones yourself, but let me give you this as exercise to do. Let me give you this as work to do, just like an assignment, and you can provide the answer in the comment box section. Let's see those of you that have tried it. So this is the assignment. Just let me know the answer in the comment box section. I'll not put the option anyway. Just tell me the answer in the comment box section. So the assignment is 100 centimeter cube. 100 centimeter cube of oxygen. 100 centimeter cube of oxygen are made to react with 50 centimeter cube of hydrogen. Are made to react with 50 centimeter cube of hydrogen. And the whole mixture and the whole reaction, the whole reaction and the whole reaction mixture. I love this question, another tricky one. And the whole reaction mixture was then passed was then passed through through a hydrous calcium chloride. calcium chloride. Full stop. What is the volume? What is the volume? What is the volume of the gas left? What is the volume of the gas left? That's the total gas left. That's the meaning. What's the volume of the total gas that is left? Okay, so what is the volume of the gas left? So this is the work to do. So you guys try that. Put the answer in the comment box section. Let us know what your answer is like. Very, very important. Let's know what you got. Just put it in the comment box section and I'll tell you if your answer is actually right or wrong. So if you are just watching this YouTube channel, kindly subscribe to this channel and click on the notification bell so that you'll be notified when I drop any video. So this is an explicit video about Avogadro's and Gay-Lussac's law and a lot of examples that can help you. So thank you guys. Till we meet again. I love you. Thank you. God bless you. Thank you.